Hi, I'm Cameron, and this is Lab 5 Slinky Drop. The purpose of this lab is to evaluate the motion of the top of the slinky and determine if it demonstrates the law of conservation of energy. Some of the fundamental principles of this lab is Newton's second law, which explains that an object will accelerate if there's a force acting on it. In this case, we will use a velocity update formula, which will help us find the new velocity of our system. Another fundamental principle is Newton's first law, which states that an object will stay in motion until a force acts upon it. This includes a position update formula, which will help us find the new position of the system. And the last principle is the energy principle. This states that the total energy of a system is the sum of the work and heat of its surroundings, but it's also the sum of the changes in energy of the system. The energy equation for this experiment is gravitational potential energy, which is the mass times the acceleration due to gravity, and the change in y position. Next is the kinetic energy equation, which is 1/2 times the mass times velocity squared, and last is the spring potential energy, which is 1/2 the spring constant times s squared, s being L minus L naught. The initial conditions on the screen are using the code to model the experiment. Most importantly, the system is the slinky and the earth, and there is nothing in the surroundings. The spring constant was found online from the Physics of a Falling Slinky webpage and was found to be between 0.80 and 0.84, and I chose 0.84 for this experiment. L naught was approximated by using the average height of a man and where the slinky fell in comparison. For my approximation, the slinky fell 3/4 of the way down, so I subtracted the remaining 1/4 from the height of the man. Next is the video that I analyzed. In this video analysis, I chose to use the hand as the attachment point and have L hat point in the downward direction. Here I only have the loop of my experiment because the other parts of the code are the initial conditions and formulas I explained in the previous slides. In this part of the loop, I set my initial energy variables equal to the energy variables I created from the equations I explained in slide 2, which we will see farther in the loop. I kept my gravity and spring forces in vector form and added them up to make my net force. I used the position and velocity update formula to update the position and the velocity, and I redefined the spring force components. In the second part of this code, I redefined the energy equations and created the change in energy variables by setting them equal to their final energies minus their initial energies. And that's it for my code. As you can see by the graph, my results support that the system does follow the law of conservation of energy. The orange line indicates the change in total energy of the system, and it consistently remains at 0 the entire time. For those who are not familiar, the law of conservation of energy states that the total energy of the system is conserved as long as no work/outside forces act upon it. There are not many comparisons to make between the model and the experiment. However, some similarities are that the energy principle is consistent in both, and some of the differences is that the experiment has some drag forces that are not included in the model. For the additional questions, what if the man holding the slinky applies a downward force on the slinky? If the man applies a force on the system, he is doing work on the system. As mentioned before, energy is conserved if there is no work done on the system. However, in this case, since work is done on the system, energy is not conserved. What does it mean if the amplitudes are large or small? Simply put, large amplitudes demonstrate higher energy and small amplitudes demonstrate lower energies. In this experiment, potential energy of gravity has the highest amplitude, so it has the greatest energy, and spring potential energy has the lowest. Spring potential energy is also the most inconsistent because at one moment, the spring collapses on itself and there's no longer spring potential energy. Lastly, the errors in my experiment are as followed. The variables in the experiment, like the spring constant and the length of their slinky, were not known. They are approximations and as such are not as accurate as the real data. These approximations could have affected the code and the experiment data. Plus, when taking the data from the video, at some point the background and the slinky were of similar color, and it was hard to pinpoint the correct location of the slinky. This could have caused an inaccuracy of the points given by tracker. Thank you for watching my video.